Here's the next part to your work, energy, and power section of notes on topic 2. So this section is going to be on the work-kinetic energy theorem and then possibly going into different forms of potential energy. But first we have work-kinetic energy theorem. Well, once again, in order for there to be work, energy has to be used. Obviously, the object's in motion to say that you're doing work because F and D have to be parallel to each other, which means that you have to have some displacement, because if displacement was 0, then force would be 0, which means your work would be nothingness, right? So you have to have some displacement that you are traveling in order to say that you are doing work. Therefore, it's called the work-kinetic energy, not potential energy theorem. What I'd like you to write down for the definition here is net work done by all forces acting on an object equals the change in the object kinetic energy. So right there it's telling you W net equals delta KE, right? The network, W net, the change in the object's kinetic energy, delta KE. So the equation we're going to look at with this is W net equals delta KE. We'll have to do F net D cosine theta equals KEF minus KEI. All right? Next thing that we have then is talking about mechanical energy. Mechanical energy is the energy required by the objects upon which work is done. It's energy which is possessed by an object due to its position or motion. So long story short, what the owl is telling you here is mechanical energy is the ability to do work. There are two different forms of mechanical energy. You should be familiar with these. The first form of, well, let me reinstate this, guys. ME, capital M, capital E is the abbreviation for mechanical energy. Okay, so you have two forms of mechanical energy. You have potential energy, and you have kinetic energy. Yeah. Whoops. Furthermore, you're going to have different flavors of potential energy, so please don't think that although we're only listing two forms of mechanical energy, that's it. It changes. So one thing that we can look at here is this wrecking ball on this crane is going to strike this building. The wrecking ball is currently at rest. Now it's in motion in the middle slide, so it's doing work, right? What is it doing? It's destroying the building. So if you want to take a second and read this blurb here, if you want to pause, read the blurb about possessing mechanical energy, its potential versus its kinetic, etc., etc. It's applying a force. There is a displacement, therefore W net could be solved for throughout this system. Long story short, W net equals delta KE, work kinetic energy theorem. So another example here is at the bowling alley, you roll the bowling ball down the lane. It has kinetic energy. It strikes those pins that are currently at rest, and then they begin to start moving due to this. So there was a force that was applied. They moved a distance, so you could solve for the work. You also know the kinetic energy prior to and after the collision. So this would be another example of W net equals delta KE. You could also incorporate momentum in here, right? And collisions. So you could talk about the type of collision that was experienced here and how much momentum was conserved or lack thereof based on the idea of momentum. Obviously, based on which type of collision, you could tell me then if energy was conserved or not. Okay, so moving right along. For the equation here, I never really come out and say it for a slide, so let's just jot it up here real quick. W net equals delta KE, okay? Whereas delta KE is KEF minus KEI, whereas KEI would be 1/2 mVI squared, and KEF would be 1/2 mVF squared. It could be safely assumed that your mass is not changing as the ball was rolling down the lane, or the pins weren't losing any mass, nor were they gaining any mass, stuff like that. So m is going to be your constant. So you're concerned about your initial and your final velocities. So we can kind of think of this really long-handed here. W net equals delta KE, whereas W net is F net D cosine theta equals KEF minus KEI Potentially your F net would break down into MA net. You would then need to be specific in the X direction or in the Y direction, times D times cosine theta equals 1/2 mVF squared minus 1/2 mVI squared. Rearrange, plug in, solve through, etc., etc. So think of this equation as the work that an object can do while changing speeds, right? Because if its speed was constant, then your kinetic energy would be 0, right? Because your initial velocity would be 0. Therefore, KEI would get hacked off, right? Okay, cool. So then number 2 says the amount of energy stored in the motion of an object. So those bowling pins that were initially at rest, they'd be talking about the potential energy throughout them. So these two blurbs right here aren't necessarily using the entire idea of the work-kinetic energy theorem, because obviously for the second one it'd be equal to 0. But it is looking at kinetic energy and the difference between KEF and KEI. So remember on this one, when using this equation, you must include all forces that are working on the object. So you got to use KE and PE. If there is no friction, I added this, guys. If there is no friction in the system, then you could say that there is 100% transfer. Check this out. No matter where you are on this system, you equal 50,000 joules, right? Because there's complete transfer of energy throughout the system. Why? Because it's on a frictionless plane. Next, so you're going to try some examples of KE versus PE. Please click on this right here and work on a few of these examples. Haha, work on a few of the examples? Okay. So anyways, coming down here, you get a nice little blurb about this. Here's a big misconception right here. So make sure you read about that. And then here's some examples right here. A ball falls from a height of 2 meters in the absence of air resistance. KE to PE or PE to KE. So what was the ball doing? What is it currently doing? So that would be an example of PE to KE. The ball is losing height, it's falling. So PE to KE, it's gaining its speed. So then just go through and discuss a few more of these examples, guys. Please, on your own time, go ahead and do that. Here's some more of these descriptive type ones here. Lots of examples for you to look at. There's an animation for you to follow as well. All right, back to our notes here. So with this on our sample problem, we go into this knowing that we have a mass of 10.0 kilograms. You have an initial velocity of 2.2 meters per second. You have a final velocity of 0 meters per second. You have a mu k of 0.10. You have a theta of 180 degrees. And you are trying to solve for how far does this object move. So you have W net equals delta KE, because that is the equation for the work-kinetic energy theorem, whereas your W net is your F net times D times cosine theta, which equals your KEF minus your KEI. Well, you don't know what F net is, but you know based on this picture that you're talking about a frictional force. So your frictional force is going to break down into mu k, mg, d cosine theta. Your KEF cancels out because your VF is equal to 0. So you just have a negative 1/2 mVI squared. Make sense? So now we want to rearrange this whole thing by dividing by mu k mg cosine theta. So we can get d all by itself. So d equals negative 1/2 mVI squared all over mu k g cosine theta. Sorry, UK mg cosine theta. Well, m's cancel out. You don't even need them there. So we're really using negative 1/2 VI squared over mu k g cosine theta. I'm going to go right here just so we can save some room. So you have negative 1/2. Your VI was a 2.2. That's being squared. Your mu k is 0.10. Your g is 9.81. And your cosine theta is 180 degrees. So plugging that into your calculator, please do so at this time, guys. You should get a calculator answer of, plug it in, 2.5 is what you should be seeing. you only want 2 sig figs, so your distance does equal 2.5 meters, or 2.5 times 10 to the 0th meters for your final answer there. Okay, so then putting it all together with work-kinetic energy theorem, you do not have this worksheet yet, so don't worry about that at this time. I would like you to work on your W net equals delta KE worksheet, those like 3-4 problems that you have. This video here is pretty cool for you to watch, just to get the idea that it shows the breakdown, like using forces and stuff. It's pretty sweet. Okay, so I'm going to stop right there and do a separate video on potential energy.